All right, today we have our last two minor gas laws to talk about. We're going to do two of them today because you're probably pretty used to the format of how the equations are set up and how the story problems are set up. So rather than take 2 more days to do the last two, we're just going to do them both today. So your worksheet tonight will be half and half. It will be half one equation and half the other. Last two minor gas laws deal with the fourth gas law variable that we haven't talked about yet. Which one have we not included? Amount. So the last two equations, or the last two gas laws, are going to have to do with the amount of gas involved. First one is called Avogadro's Law, named in honor of this gentleman here. What else do we know Avogadro for? Moles, the number of things in a mole. How many things are in a mole?
6.25 times 10 to the 23rd.
You're close. 6.02 times 10 to the 23rd. Avogadro is already famous for counting things. How many things are in a mole? So it kind of makes sense that he would be the one to be credited with one of the relationships involving an amount of gas. We measure amounts in moles, or we could even count the number of particles that were in a particular container. So Avogadro's law kind of makes sense that it relates amount and volume, which means we are not changing pressure or temperature. Also, part of the reason that we're doing two laws in one day is that these laws are pretty easy to understand. If you take a helium balloon and you put more helium inside, what happens to the volume? It increases. If you take a balloon and you take the gas out of it, what happens to the volume? It decreases. That's pretty much common sense. If you increase the amount of gas, as long as the walls are free to expand in something like a balloon, then your volume will get larger. If you decrease the amount of gas, again, as long as the walls are free to move, then the volume of that container would decrease. We can be a little bit more specific with our explanation as to why does that occur by saying that more gas particles would take up more space. Again, it's kind of common sense, but it's a little bit more specific than what we just said. The opposite, of course, is also true. Less gas particles take up less space. What kind of relationship is this? Is this a direct or an inverse relationship? Direct, because both things change together. More gas, more space. Less gas, less space. Direct relationship. So what's the equation going to look like? Divided or multiplied? Which one? Divided, because it's direct. You might remember Charles' law was also direct, and that was divided. Gay-Lussac's law was also direct, and that one was divided. So far, the only inverse relationship we've had was Boyle's law, and Boyle's law is P1, V1, so that's multiplied. So this one is also going to be a divided equation. V1 over N1 equals V2 over N2. We still have the before case and the after case, just like we're used to. Story problems will be set up just like you're used to. The only thing we've changed is the variables that we're looking at. So let's do our two examples. 5 liters of a gas is known to contain 0.965 moles. If the amount of gas is increased to 1.8 moles, what new volume will result? If you're not sure where to start, make a list of what you have and what you're looking for. We know that the first volume is 5. The first amount of moles is 0.965. The second amount of moles is 1.8. And we're looking for the second volume. We also know that our volume will come out in liters because that's the unit that we're putting in. Whatever unit you put into the problem is the one that you get out of the problem. Once you know what you have and what you're looking for, plug your numbers into your equation. This is the step that I would need to see on a test or a quiz. Where did your numbers go? And from here, it's just algebra. Cross multiply and divide. to solve for V2. So you would take the 5 times the 1.8 and V2 times 0.965, and then you would divide both sides by 0.965. How many sig figs should we keep? 3. Go back to the numbers in the question, and we'll keep 3. Answer should come out 9.33 liters. Again, your answers may come out just slightly different depending on how often you round during your math. If you stop and round at each step during your math problem, your answers are going to be a little bit different than if you carry numbers through on your calculator until the end. Second example. 1.5 moles of a gas is contained in a 2-liter balloon. When some gas is removed, we don't know how much, the volume decreases to 1.43 liters. How much gas was taken out? Again, if you're not sure where to start, make yourself a list of what you have and what you're looking for. We know that the first amount of moles was 1.5. V1 is 2 liters. We're solving for N2. What's the second amount of moles? And the second volume was 1.43. Then, just like before, plug your numbers into your equation. This is the step I need to see. Where did your numbers go? Cross, multiply, and divide, just like before. We'd have 2 liters times N2, 1.5 moles times 1.43 liters. Simplify your numbers on the right. Divide both sides by 2. How many sig figs should we keep? 3. Most of the time, this is the final answer. But what does the question ask you for? Go back and look at the question. What's it ask you for? How much was taken out? What does this tell you? 1.07 is still inside. 1.07 is how much is still left inside. What should we do to figure out how much was taken out? 1.50 minus 1.07. So on these, you have to be a little bit careful. Watch the wording. What does that question actually ask you for? N1 minus N2 will tell you how much gas was removed. So 1.50 minus 1.07. Remember, when you're subtracting, you count decimal places on your sig figs. So we'll keep 2 decimals. Final answer on this question is 0.43 moles were removed. Okay, next law. Doesn't have a name. The poor orphan gas law, it does not have a name. Called the other law for our purposes. This will be the last minor gas law that we'll do. And one of the last combinations of variables that we could use. This one relates amount and pressure, which means we are not changing volume or temperature. The relationship for this one is pretty well common sense, just like the other one was. Think about inflating a tire. If you put more air into a tire, what happens to its pressure? Goes up. If you let the air out of someone's tires, what happens to their pressure?
Their blood pressure will rise.
Very funny. The pressure would go down. So again, this relationship is pretty much common sense. If you increase the amount of gas, the pressure will increase. If you decrease the amount of gas, then the pressure decreases. We can be a little bit more specific than this when we look at why this relationship is true. To understand why this relationship is true, we need to remember, what is pressure caused by? Collisions of molecules with the walls of their container. Pressure is caused by collisions. If you have more particles, then you have more collisions. More collisions means more pressure. So why does this occur? More molecules cause more collisions, more pressure. And the opposite is also true. Less molecules would cause less collisions, which means less pressure. Is this a direct or an inverse relationship?
Direct.
Direct. So what's the equation going to look like? Divided. P1 over N1 equals P2 over N2. Side note, we've practiced these problems for quite a while now. So you may start to see some twists and turns on your homework, such as if you are given two pressures in different units, what do you have to do before you start? Convert one to the other. It doesn't matter usually which way you go, but remember that your pressure units have to match before you put them into the equation. Another little twist that you might see, what if you're given an amount of gas in grams? Change it to moles before you start. Hopefully by this point of the year we remember how to do that. Look at what the gas is, look at the periodic table, add up the pieces if you need to, change your grams to moles before you put it into the equation. Okay, a couple examples and then we'll be done. 0.58 moles of a gas exert 50 kPa of pressure on a container. If a gas is added until there is 101.3 kPa of pressure, how much gas is in the container now? Check your pressure units. Do they match? Yeah. So there's nothing tricky about this first problem. If you're not sure where to start, make yourself a list. What do you have and what are you looking for? The first amount of moles is 0.58. The first pressure is 50. The second pressure is 101.3. And we're looking for the second amount of moles. Once you know what you have and what you're looking for, plug your numbers into your equation. Remember, that's the step I need to see. Where did your numbers go? And from here, it's just algebra. Cross, multiply, and divide. 50 times N2 is equal to 101.3 times 0.58. Simplify the numbers on the right. Divide by 50 from the left. How many sig figs should we keep? 3. Go back to the numbers in the question. We'll keep 3. Should get 1.18 moles, again, depending on how many times you round. If you round at every step, your numbers may come out a little different than if you carry a number through on the calculator all the way. Last example. 5 moles of a gas is contained in a 3.5 liter cylinder. Do you need to add the 5?
Yeah.
Okay, add the 5. Add the 5 to your story problem. If 2 moles of gas were removed and the pressure dropped to 1.25 atmospheres, what was the original pressure in the cylinder? What's N1? 5. What's P1? We don't know. We're looking for it. What's N2? 3. Did you catch that?
Yeah.
Did you catch the subtraction?
Yeah, it was 5 moles.
5 moles to start with. 2 moles were removed. How much is still in there? 3. 2 moles of gas were removed. How much is still in there? 3. Pressure dropped to 1.25. We're looking for P1. Now that we know what we have and what we're looking for, we can plug our numbers into the equation. And this is the step I need to see. Where did your numbers go? From here, cross multiply and divide, just like we've done every other time. 3 times P1 is equal to 1.25 times 5. Simplify the numbers on the right. Divide by the 3 from the left. How many sig figs? 3. Units are? Atmospheres, because that's what we plugged in. You should get 2.08 atmospheres. Again, depending on how many times you round. Homework for tonight is a worksheet. Tomorrow we have a lab. And then we have one more set of notes to do on Wednesday this week.